Hello everyone. Today our speaker is Agniva Chatterjee. He is a Ph.D. student at IISc Bangalore working with Professor Purvi Gupta. His research interests lie in several complex variables, function theory and convex analysis. This is the first talk in the series, a brief introduction to SCV. Today Agniva will talk about the similarity and differences between one complex variable and several complex variables. Over to you, Agniva.
Yeah, so first of all, thank you very much to the other organizers for giving me this opportunity to speak. So first of all, I'll start with a disclaimer. The disclaimer is that so Intro to SCV is basically a semester-long course, so it is not possible for me to cover every aspect of it in just 4 lectures. So the main goal over here is to just briefly introduce the central objects that play a very important role in several complex variables, and we'll talk about differences and similarities between the analysis of the one complex variable, and which I hope that everybody has seen. And we'll introduce things in several complex variables slowly. And I will try to give, I will skip a lot of proofs, and I will give the proofs that I will give is very like a sketchy sketch of those proofs. The point is that you can always, I'll refer some references. You can always go back and take a look at those references. So without further ado, let's start. So today's lecture is all about more or less complex analysis. So it's very less several complex variables that is going to happen. And mostly the several complex variable that is going to happen in today's lecture is basically we sort of go side by side with complex analysis. So I'd like to start with, in fact, complex analysis to jog up your memory, what complex analysis is all about. So this is a very interesting question. So uh, complex plane is nothing but R2, right? I mean, they are the same. The underlying set are basically the same. But I think everybody has seen that the real multivariable calculus on R2 is strikingly different than the complex analysis or calculus in uh, complex plane. For example, I think you have already seen these things, that a function which is one time real differentiable may not be twice differentiable. But if a function is holomorphic, which is complex differentiable, that automatically becomes a smooth function. In fact, more, it becomes uh, complex analytic. And on the other hand, for example, smooth cutoff functions does exist. That basically means that smooth compactly supported functions exist in R2, but there are no holomorphic compactly supported functions, because holomorphic functions, the zeros of holomorphic functions are just discrete, right? That's the identity principle. So you can see that there are striking differences. You can find more and more striking differences in real multivariable calculus and complex analysis. So my question to all of you is that uh, what are the reasons, or the sort of the main reasons behind such differences? I mean, what is the main reason that analysis in R2 and analysis in C is so different? And I think you probably know the answer, is that C is an algebraic field. R2 does not have a field structure unless and until you give the field structure of C. So that's the main difference. And this algebraic means that every polynomial in complex plane can be factorized, right? So that's the main reason why complex analysis is so vastly different than the analysis in multivariable calculus, or real multivariable calculus. Now, let's jog up your memory a little bit more. What are the definition of holomorphic function in complex analysis? We're just talking about complex analysis. No several complex variable has been introduced. So here, a function f, suppose it's defined on an open set omega, and it's a subset of C to C. Then f is said to be holomorphic if for each a in omega, this quotient, limit of this quotient actually exists. Now, the important point to notice over here, because they are complex numbers, so f of a plus h minus f is a complex number, and h is also a complex number, I know how to divide two complex numbers. That's because of the field property. So this definition is actually legit, right? But if I really go to R2 to R and want to define this exact definition, if you want to mimic the definition, I cannot do that, because if I have a function from R2 to R or R2 to R2, I cannot do this definition. I cannot mimic this definition because I don't know how to divide a tuple of R2 with a tuple of R2, because this division is not legit. So what is a way out? I think this is all everybody has seen, is that to define differentiability in R2, we need to introduce this R linear map, which is basically consists of the partial derivatives. And in then you have to say that, okay, this quotient goes to 0. Then we say that the function is total derivative or differentiable. So that's the difference between the complex analysis and the real analysis, like the R2 analysis I said, because this division is so important. And let's now go back to holomorphic functions in complex plane. I think everybody has seen this, is that holomorphic function is same as complex analytic functions, which basically means that they have local power series representation. So the function has a local power series representation, the function is holomorphic. Another definition or another equivalent condition of holomorphicity is that Cauchy-Riemann equations, right? So at each point in omega, if the CR equation satisfies, then that function is actually holomorphic. So what is CR equation? It's basically some relation between the partial derivatives of the real part of the function and imaginary part of the function, which is del u del x equal to del v del y and del u del y equal to minus del v del x. All right. So that's the starting point of complex analysis. Now, if I want to go to several complex variables, the first starting point and the first question one should ask is that how to define holomorphic function in higher dimension. Because the problem over in higher dimension is that Cn is not a field. So you are facing the same problem as Rn, that you are not able to define this quotient because this division will not be legit if I allow H to be in Cn. So you cannot do that. So what is the way out? Right. So the question is, how do you define holomorphic function in higher dimension? So that's the sort of main point of today's lecture. So what we are going to do, we are going to give three proposals of holomorphic functions in Cn. Before I start, I want to make a small notation. I think this notation will, it's a very standard notation in several complex variables. So whenever I say function, the word function, that basically means, this means that the range of the function is a subset of C. So it's not Cm. So basically I'm talking about functions which are from Cn to C, not, the range is not high dimensional. We will not talk about too much about when the range is a subset of Cm. Those are called holomorphic maps, but we will not talk about too much about them. So let's talk about the three proposals. So the first proposal, so proposal one, and this proposal actually motivated from certain analysis that I have already talked about. So this is motivated from real multivariable calculus. Real multivariable calculus. So how do you define the whole differentiability in Rn? Differentiability of a function in Rn. What we did, as I already presented this, that you bring this R linear map, right, which is just consists of the partial derivatives, and then say that this quotient goes to 0. So if I want to mimic this definition in higher dimension in Cn, what I would, the natural change that I would do is that I just replace this R linear by C linear. That's it. Okay. So a function, so f from open set in Cn to C is said to be holomorphic. Said to be holomorphic if for each A in omega there exists a C-linear map D, which I'm just representing as DCFA, from Cn to C. This is C-linear, such that this quotient goes to 0. So I'll just exactly mimic the definition. F of A minus H minus Fa minus DC Fa dot H divided by norm of H. This quotient goes to 0. So here, just to, as H tending to 0, just to be sure, H is in Cn, by the way. And this is, I think you believe this definition is exactly, I have just mimicked the definition from the real multivariable calculus. All right. So the next one is, the next proposal is actually motivated from analyticity, from C analyticity. What do I mean by that? Well, I think everybody, I told a few minutes back that in one complex variable, holomorphic functions are same as complex analytic. That basically means they have a local power series representation. But I know how to define power series in higher dimension. So what I'm going to say that the function is holomorphic if it has local power series representation. That's it. So that's just mimicking the analytic definition of holomorphicity in of complex analysis in higher dimension. That's what I'm going to do. So F from omega an open set to Cn to C said to be holomorphic if for each A in omega there exists a neighborhood. So local means that you have a neighborhood UA, neighborhood in omega, such that F can be represented as a power series. So n to the n A alpha z minus A whole to the alpha for all z in UA, where these are standard notation in multivariable calculus, where alpha is an n tuple in natural numbers and z minus A whole to the alpha basically means that z1 minus A1 whole to the alpha 1 times z minus A1 to the alpha n, zn minus, zn minus an to the power alpha n. And what about this convergence? What is the convergence of the, what is the mode of convergence of the right hand side? And the right hand side converges absolutely. That is the norm of this terms, absolutely and uniformly on compact subsets. Uniformly on compact subsets of UA. So I've just mimicked the definition of C analyticity. That's it. I think this is also quite believable. Next up. So next one, proposal 3. This is motivated from CR equation. Now there is a catch over here. Okay, so let's go back to CR equation in one variable. So in one complex variable, CR equation basically means that it satisfies this relation, right? That the partial derivative satisfies this relation. Now, when you are in higher dimension, so in Cn to Cn, Cn to C, how many partial derivatives you have now? You have 4n many partial derivatives, right? If f is u plus iv, then you have du del xj, du del yj, dv del xj, and dv del yj. So you have 4n many. So there are 4n many partial derivatives now, real partial derivatives. And you need to mimic a condition like this. Now, what is a natural that comes to your mind? What is a natural condition that appears to your mind? Is that you just do it at each pair, like at each variable, basically, which basically means, what I mean is that you just do this, that du del xj is equal to del v of del yj, and del u del yj is minus of del v of del xj for all j from 1 to n. So for each j, I am just mimicking the CR equation for each j. What does it mean, basically? This means that if I consider this function, so I have an a, which is a1 to an, and if I just consider this function gz, which is j, which is defined as, I fixed all the coordinates and free the jth coordinate. So it's the jth coordinate. I defined a one variable function. If I consider this function, then del f or del u del xj equal to del v del yj, and del v del xj equal to minus of del u del yj. This means that this implies that gj is holomorphic. This is a one single variable function, and the Cauchy-Riemann equation satisfies basically means that gj is holomorphic. So what I am actually saying over here is that this condition for all j implies that your function f is separately holomorphic on each variable. So let's write down properly. So the proposal 3 is f, again the similar setup, open to Cn to C, is said to be holomorphic. Said to be holomorphic if for each a in omega, a equal to a1 to an in omega, this function gjz, which is defined as f of a1 at the zth variable to an, is holomorphic on this particular set, which is all, it's a subset of C, such that these guys are in omega. Basically, basically what I'm doing over here is that geometrically I'm doing something like this. This is your point A, say A1 and A2. Just look at C2. So this is your omega. What I'm looking over here is that I'm fixing A1, and I'm just coming via this line. And similarly, I'm fixing A2 and then coming via this line. So it's basically partial derivatives. So this basically means that, so this is same as complex partial derivatives. Complex partial derivatives exists, or rather all complex partial derivatives exist. And this is same as the CR equation satisfies in each variable. Each variable Z1 to Zn. And this is same as saying that F is separately analytic, separately holomorphic. That you fix one, you fix just one, you just vary one variable and fix the rest of the variable, and that function is holomorphic. Now, you should have a complaint about this definition. So when I'm asking that this is a definition, then basically what I mean is that this proposal 3 should be equivalent to proposal 2 and proposal 2 should be equivalent to proposal 1. So all of these three are, they should be equivalent because they are all definitions, right? But the issue over here is that let's go back to the real multivariable calculus. So in real multivariable calculus, partial derivative exists. Does not even imply continuity. The function is defined from R2 to R. All the partial derivative exists does not even imply the continuity. This is famous example of fxy equal to xy by x square plus y square. I think everybody has seen this. When it's non-zero and 0 at 0. This guy, the partial derivative exists at all points, but it's not continuous at 0. What I'm doing over here, what I'm saying over here, is that it is enough for holomorphicity to exist all the complex partial derivatives. So there is a counterintuition happening over here, right? My point is it too counterintuitive? Question is it too counterintuitive? Okay. So in real multivariable calculus, partial derivative exists does not mean it's continuous. But if I assume an additionally an extra condition that partial derivative exists, plus I additionally assume that the partial derivatives are continuous. In that case, if I just assume this, in that case, F become C1 in R2. I hope you remember this. It's a classic fact in multivariable calculus. So the partial derivative exists, and partial derivative being continuous implies that the function become continuous, in fact, continuously differentiable. Now, what I'm asking in complex setting, or whatever the proposal 3 is, I'm saying that if del f del z1, del f del z2, all these complex partial derivatives exist, then F is holomorphic. Okay. So here what happens? What is del f del z1? Del f del z1 is a complex derivative, right? It's a derivative of a one variable function, or a complex derivative of a one variable function. So that means this guy is C infinitesimal. In fact, complex analytic, C analytic. Because they are complex derivative of a holomorphic function. So they are in fact holomorphic. These guys are holomorphic in one variable. So you are getting this continuous condition freely here. So at all the partial derivatives here are not only continuous, they are all holomorphic. So it's not too counterintuitive to give this definition that all complex partial derivatives exist. So that's about the three definitions. So proposal 1 is just this quotient definition, which appears as a motivation from real multivariable calculus, where we introduce this C linear map. Proposal 2 is all about power series. So it's just local power series representation or C analyticity. And proposal 3 is just satisfying the CR equation in each variable. And this is probably the most sort of powerful way of checking holomorphic functions, because you just need to check that certain partial derivative satisfies certain conditions. Examples, quick examples. All complex polynomial in Cn, like A alpha to Z to the alpha. These are all holomorphic. This kind of functions like sine Z1, Z2, these are holomorphic. Uh, I mean, the point over here is that how do you check these are holomorphic? You just apply the Cauchy-Riemann equation, because you can immediately see that they are holomorphic in each variable. So they are holomorphic. Number 3, this isn't good. I mean, you can take it as an exercise. So Z1, Z2 divided by Z1 square plus Z2 square. I just complexify the last example when Z1, Z2 is not 0 and 0. I mean, it's sort of a brain teaser. Z1, Z2 equal to 0. So I said that the complex partial derivative exists basically means that things are holomorphic. Here, by the way, the complex partial derivative does exist at 0, because in fact it will be 0. You can immediately see. But this can't be holomorphic because this is not even continuous, this is not even continuous in real variable. So if it is not continuous in real variable, it can't be continuous in complex variable. So what is the gap, or what is the gap between it? So you just find it. So this is not holomorphic. Another little bit of nice exercise. Find a holomorphic function from C2 to, or subset of C2, to C, which has exactly 20 non-holomorphic points. So can you find a function with finitely many holomorphic points, basically? Finitely many non-holomorphic points. That's what I'm asking. Think about it. It's not very easy, but just think about it. All right. So that's more or less all about the definition. Now, how do you prove these three equivalence of these three definitions? So equivalence of these three definitions. Equivalence of these three definitions. So maybe I just wait for a couple of seconds. Is there any question? All right. So equivalence of these three definitions. So the way it goes is that it goes as 2 implies 1, 1 implies 3, and 3 implies 2. Now 2 implies 1 is straightforward. Why? Because 2 is the analytic definition. If you have a power series out of C analytic function, that is differentiable. It's the same proof as the real variable case. If you have a C analytic function, it's smooth. In fact, smooth. Not only the one-time differentiable. So that's a straightforward proof. 1 implies 3, that if this quotient definition satisfies, that basically means that the Cauchy-Riemann equation is true. Now, this is not very difficult. So this is similar. To the one complex variable Cauchy-Riemann equation. So in one complex variable Cauchy-Riemann equation, how you actually prove it? You just come from one time, you You take this quotient and you one time you go from real axis, one time you go from imaginary axis, and you get the result. Here you also have to do the same. The only thing you need is that you need a form of this you need a form of this C-linear map, which will consist of certain partial derivatives, and then you can find the relation between the partial derivatives. The important part is this part. So this is the key part. That if the Cauchy-Riemann equation satisfies, or rather it's holomorphic at each variable, that implies that it's C analytic, or it has a power series representation. And to prove this, you need a key tool which also appears in complex analysis, and probably to me it's the most important tool uh, in complex analysis, and it's a formula actually. So this is the Cauchy integral formula. I think if you go back to complex analysis and look at the theorems, you will see that almost at every theorem Cauchy integral formula appears in some form. So what does Cauchy integral formula says? So it says that in C
Agniva,
basically. So yes,
so just one question.
yep.
So is there any characterization for this C linear map from Cn to C, like we have in?
Uh, I am here defined it for Cn to C. If you go for Cn to Cm, that is also there is a.
No, I'm asking that is there any characterization for C linear map from
Hmm.
Cn to C? Like we have C linear map from C to C is of the form alpha into Z. I'm just asking.
Ah, okay. Okay. That I need to think. I think you can send the basis to basis. That sort of, because C has
Yeah,
only
so I
one
was
basis,
just
so you can do that, I
yeah.
guess.
Okay.
You just send the basis to basis, and then you have to check that when that will be C linear.
Okay. Okay.
Yeah,
Thank you.
yeah. So what is Cauchy integral formula in one variable? So if you have a holomorphic function, this is holomorphic, and if you take a disk whose closure is inside omega, then you can represent the function, the value of the function, using a boundary integral. That's what it means. Is f zeta by zeta minus z d zeta. I think everybody has seen this. And z is here so z is here in inside the disk. Now, what is a version of Cauchy integral formula in higher dimension? This question is quite interesting. So version of Cauchy integral formula, which I will denote as CIF in SCV. The first question that one should ask is that here, in the one variable case, I was doing it for the disk. What is the correct analog of disk in the higher dimension? Well, one choice is, of course, the topological ball, right? That's the BAR, which is just a topological ball. Is it all Z in Cn such that Z minus A norm of this is less than R? This is a topological ball, which is ball. There is another option, by the way, and that is just take the product, the n Cartesian product of disk. So D A1 R1 cross D A N Rn. So these are called polydisk. They're represented like this. So the representation, so it's a very painful to represent things in higher dimension, because you're starting at C2, right? C2 is 4-dimensional. You cannot represent, you cannot draw 4-dimensional things. So what we do sometime, we sort of draw them in mod Z1, mod Z2 axis. I mean, this mod Z1, mod Z2 axis will probably appear again in the next lecture. Uh, So you can always, you can't always, in fact, represent them in mod Z1, mod Z2 axis, but in this case you can. So this domain is the unit ball. So this is just mod Z1 square plus mod Z2 square less than 1. This domain over here is the unit polydisk. So this is nothing but just the unit disk cross the unit disk, because I have just defined it in mod Z1, mod Z2 axis. So this is the unit disk, so which is basically mean the maximum of mod Z1 and mod Z2 axis is less than 1. All right, so you can see that there is a distinction between the ball and polydisk. It turns out for a Cauchy integral formula, this behaves better. This behaves better for Cauchy integral formula. So let's write down the Cauchy integral formula. So this is a theorem. And probably the first theorem is the Cauchy integral formula for polydisk. Polydisk. Sorry. Cauchy integral formula for polydisk. So what does it say? It says that if F is omega subset of Cn, open set, to C, a function which is separately analytic. Separately analytic basically means, I have already explained this. Separately analytic means that at each variable, it's satisfying the CR equation. Analytic. And so it's a delta AR is a polydisk. So it's defined as D of A1 R1 cross D of AN Rn. And this polydisk is a polydisk such that the closure of the polydisk is inside omega. So what I'm doing over here is that I'm taking a domain omega, and I'm looking at a polydisk inside it, sort of like this, and that's it. That's what I'm doing. And if that happens, then if Z, it exactly kind of the same sort of formula you will get. So you have in integral. Now I'll explain this in a minute. P delta AR. What is this notation? I'll explain in a minute. F zeta 1 to zeta n divided by zeta 1 minus z1 times zeta 2 minus z2 dot zeta n minus zn. D zeta 1 up to d zeta n. So what is this integral? What I'm what is this? What I'm actually integrating over is that this is actually not the boundary of the polydisk, by the way. So I go back to the picture of the polydisk. The boundary of the polydisk is this whole thing, this whole blue portion. What I'm actually integrating over is basically a torus, which is just this thing. So this point is mod z1 equal to 1 and mod z2 equal to 1. So at this point, it's basically a torus. It's circle cross circle, right? Circle cross circle. So I'm integrating over that. So this B, so this where? So okay, so Z is in delta AR, and where B D delta AR is just product of circles. So this is just product of this circles, that is the boundary of this disk. So this is known as the distinguished boundary. It's called distinguished boundary. So this is the theorem that you can actually represent any function which is separately analytic like this. And as we know that now that the separately analyticity is holomorphic functions, are basically the holomorphic functions the same, so you can represent holomorphic functions like this. But again, this is a local statement, by the way. You cannot do this globally on omega. You have to go to a smaller polydisk and then you can do it. So the point over here is that once you prove this, 3 implies 2, the equivalence of the definition become easy or straightforward rather. So 3 implies 2. Now 3 implies 2 is straightforward. Why? Okay, you have this 1 by zeta 1 minus z1 over here, or 1 by zeta j minus zj here. So you can just write them as follows. You just write them, it's just a basic calculation. You just get this zeta j 1 minus zj minus aj divided by zeta j minus aj. You just write like this, and then because zj minus aj divided by zeta j minus aj is less than 1, you just break this as power series. So break this quantity, this, into power series. And complete the proof. So that's the main point. And how do you prove the Cauchy integral formula? So I'm not going to give a full proof of it. Proof of Cauchy integral formula. I mean, this is just this can be given as very sort of easy exercise. Proof of Cauchy integral formula. So there are 2 steps actually, and basically 2 cases. Assuming f to be continuous. So here I have, if I assume additionally that this function is continuous, this proof become very, very easy. Omega to c is continuous. Then this is follows from induction and just a Fubini theorem gives you the result, gives Cauchy integral formula. But if I remove this continuity assumption, then it's a bit technical. Without continuity, without continuous assumption, it is a bit technical. So look at Ormander's book, Ormander, Intro to, or what is it called? It's probably several complex variables. I will give proper references at the end. Several complex variables. At this book, it's probably you need probably 2 or 3 more steps to show that in fact that is locally continuous, if it is something like that. So that's all. So that's more or less all that I want to say. But now let's go, once you prove that, so this is, as I said, this is probably the most powerful formula in complex analysis, and in fact in several complex variables as well. It's a Cauchy integral formula. The reason why Cauchy integral formula is so important even in complex analysis is that once you have Cauchy integral formula, there are a lot of consequences of it. I mean, the consequences are enormous, right? So let's go back to, let's look at some consequences or properties that I've already written them down because they are all, I think everybody has seen this. They're all in the setting of complex analysis. So these are all basically consequences of Cauchy integral formula. So if you have a open connected set, I just assume the connected set, which is known as the domain. Many of them are even true without this assumption. So suppose you have a holomorphic function from omega to C. Omega is a subset of C, by the way, not Cn, right? Again, I'm into the complex setting, in one complex variable setting. The first one is the Cauchy integral formula. I think, as I mentioned a few minutes earlier, Cauchy integral formula is extremely important. The first one is called Cauchy integral formula. The immediate consequences of this formula is maximum modulus principle, which basically says that if you have a holomorphic function and the function is in fact continuous up to the boundary, then and of course this omega has to be bounded, by the way. So omega is bounded here. Otherwise, the maximum may not exist. So then the maximum of mod fz is same as the maximum of mod fz on the boundary. So basically, the maximum attains in the boundary, right? Then you have open mapping theorem. There's a holomorphic functions are open map. You have Cauchy estimates, which gives you estimates of derivative of a holomorphic function using the maximum of the function on the boundary, basically. Liouville's theorem, which says that bounded entire functions are constant. That's basically a consequence of Cauchy estimates. Montel's theorem, which says that the locally bounded holomorphic family is always normal. In other words, if you take this, if you know what is the open compact topology of a domain is, then with respect to open compact topology, a closed and bounded set is compact. So that's Montel's theorem. Weak identity principle, which basically says that if you have a open set and a holomorphic function vanish on an open set, then the function is completely zero on omega. This is in fact a property of any complex analytic function or any real analytic function. Next comes a structure theorem, like structure near a zero. I think in many exercises you have seen this, that this plays a very important role in complex analysis. That if you have a point P in omega where Fp is zero, then locally you can write the function as a product of a polynomial times a non-vanishing holomorphic function. I mean, this is quite an important, I mean, many exercises you will see that this appears. And next one is removable singularity theorem. So removable singularity theorem basically says that if a function is holomorphic on a domain, but a point, so except a point, but it is bounded near that point, then you can actually extend the holomorphic function. So removable singularity basically means that. And for example, sin z by z is a classic example of it, right? Where the limit at z tending to 0 exists, so it's bounded near 0. So you can extend this function as a holomorphically to omega, to any, basically in disk or even in probably C. Yeah. So now comes the strong identity principle. So zeros are isolated, right? In complex analysis, if the zero set has a limit point, the function is already constant. So zeros are discrete in complex analysis. And then one of the influential theorem is the Riemann mapping theorem. It says that if you have a two proper simply connected domain in C, they are biholomorphic. This is quite striking and quite amazing as well. So these are like more or less all the theorems that one can see at the first course of a complex analysis. There are Picard's theorem and other, which I didn't write. Now my question, or rather the point is that how many of them are true in higher dimension? So if I just replace this C to be a subset of Cn now, then how many of them are true? Well, the theorems are basically color coded. This is green, yellow, and red. And you can guess why they are color coded. So if I look at in higher dimension, all the properties that was written in green with a green heading are true in higher dimension. Now, all the properties of that are written in yellow, the exact same statement is not true in higher dimension, but there is some formulation of it. There is some modification that you can do, and then you get a sort of a same version. And all the rate properties are not true in higher dimension. They're completely false. So let's go back. So in higher dimension, as I said, you have a Cauchy integral formula, which I've just showed that. Maximum modulus principle is true. If we just replace maximum modulus principle is exactly true. Open mapping theorem is true. Cauchy estimates, you can get a Cauchy estimates. Liouville's theorem is true. Montel's theorem is true. Weak identity principle is true, which is a property, as I said, for any real analytic function. Structure of zeros, there is what known as a Weierstrass preparation theorem, which is kind of giving you a structure of zeros in higher dimension, which is not exactly like this. You need a little bit of modification. There is a removable singularity theorem as well, but you need some notion of zero set there, which maybe if I get time in later lectures, we will talk about that. There is a version of removable singularity theorem. Strong identity principle, and this is probably one of the nice example. It's completely false. I mean, there are these kind of theorems which are exactly opposite. So it says that in higher dimension, so if you have a function f from Cn to C, the zero set of f is never isolated. I mean, that is amazing. Right? I mean, it's just completely opposite. I mean, think about it. For example, what is a common example that one can give immediately of a what is the most easiest example of a holomorphic function in several variables? Well, you just take the projection. Say z1, z2 equal to z1. And what is the zero set of this? The zero set is complete this line, right? It's a complete line. And a line is not, of course, isolated. And those of you who have heard the term variety, a complex variety or any variety is never isolated, right? So zero set is never isolated in higher dimension. The Riemann mapping theorem is strikingly false, and I think every people who have worked with several complex variables have wished that if this is true, their life would have been half easier. And so the Riemann mapping theorem is false in higher dimension. In fact, the two domains that we actually saw, the two different domains, one is the ball and another is the polydisk. And they're like the two most simplest domain, and they are not biholomorphic. So not biholomorphic. Uh, there are many proofs of this now. So maybe if I get time, I'll talk about this later. So that's more or less all. I don't want to push this to all the way up to 1205. So next time, I just want to mention what I want to do in next time. So next time it's more or less all about power series. So we have already defined power series, but we didn't talk about the domain of convergence of power series. For example, in one complex variable, we know that power series will always converge on a disk. But what is the domain of convergence? Domain of convergence of power series in higher dimension. So that's the thing that we will actually look for, and we'll see that there is a very peculiar property of a domain which allows you to write any holomorphic function on that domain as a power series. And then again, this mod z1, mod z2 axis will appear. So that's more or less all. I think I should stop here. Thank you. Please, any questions?
Yeah. Are there any questions?
Agniva,
Yes.
yeah, just a general question regarding
Yep.
this Riemann mapping theorem in higher dimension.
Correct.
So, like, is there any known result or a condition on a simply connected domain in Cn which is biholomorphic to the unit ball? Like, do we have any theorem?
No, there are some. yes, there are certain theorems of Riemann mapping theorems, but they are like extremely, I think they are like extremely complicated sort of things. For example, one thing you can always do, I mean, if you take like two simply connected domain, I mean, this is very easy actually. So if you take two simply connected domain and take their like Cartesian product, and then you
Oh,
can,
that is not going to be.
yeah, that is just will work because if you have two product domains, then that will work because that's
Yeah,
just
that
coming
is.
from C.
Yeah.
But yeah, I mean there are results, but they're not like very like strikingly remarkable or something like that.
Agniva, what do you mean the Cartesian product will work? Will that be?
I'm
Do you mean?
I mean I am saying that you are just extend like you have a two simply connected domain. Uh, say you have four simply connected domain. You take Cartesian product of two and another Cartesian product of other two. Then again, because you have the Riemann mapping theorem in one variable,
Hmm.
you can probably cook up a Riemann mapping theorem. I mean, sort of a biholomorphism between those two Cartesian products.
Oh, but like
No.
Abhishek is
Is it not
fixing
possible?
what
No, no.
Abhishek is. I think
Because
Abhishek is okay. Abhishek, you continue. Sorry.
yeah, like yeah. So the first, like, my question was to get a condition when I can like confirm that okay, this simply connected domain now is
Yeah, yeah,
mappable
yeah. I
to
understand
this
your question.
variable.
Yeah, I understand your question, but
And the
I really don't know any sort of results. I have seen some results about Riemann mapping theorem, but they are like extremely, I mean, extremely complicated that I have seen.
okay. And
But
regarding
yeah,
the idea you gave regarding the Cartesian product, if you take omega 1 cross omega 2, I think
correct.
they are never going to be biholomorphic to the unit ball.
Of course. Yeah, yeah.
Yeah,
Yes, that of course because that will be biholomorphic to the polydisc. I was talking about
yeah,
the
exactly. Yeah.
yeah, of course, yeah.
Okay, I was just.
So, is it a necessary condition that suppose any domain in Cn, if it is biholomorphic to unit wall,
Hmm.
then the distinguished boundary and the topological boundary has to be same. They have to be same.
Uh, yeah, I think so.
What is the distinguish? What is the concept of distinguished boundary for general domain? Like it is for polydisc and like Cartesian product kind of thing.
No, I mean, okay, so distinguished boundary in general, I don't know how to define. I mean, it's polydisc you can define, and similarly
Yeah.
probably define for the product domains.
No, you
Just
can
take
define
the
it for any bounded domain.
any bound. How do you define them? It's just maximum modulus principle. Where does it?
Yeah, the maximal boundary where you know you take the all the closed set where every function in the continuous algebra is attaining its maximum,
Yeah,
and then
yeah,
you take the minimal of such set, the
correct.
intersection of all such set.
So it's like where which is the sort of the
Okay.
smallest portion of the boundary where the maximum actually
Uh,
attains.
yes, exactly.
Yeah,
Okay.
so that is how I mean operator
And it
theory is defined.
exists. I think it's a result of Silo. It is also
Okay.
called
Ha.
Then
Silo
that is
boundary,
quite striking. Yeah.
and it is I mean it is not generally defined with respect to only with respect to a domain. It is with respect to a domain and an algebra, but when we define it with respect to a domain, the algebra is usually the holomorphic in the domain which uh, extend continuously to the boundary.
Yes. Yeah.
Okay. Okay. Thank you.
Yeah, any more questions? Okay, thank you for the talk.